Oops, I guess it will work out if I hook up the projector. Right? I was working with Mr. Foster. If you're in the AUT 104 class, you need to go to room book 6, which they're going to probably move you to 204. So if there's nobody in 206, go to 204. Power. And power is what? Well, what is it? If you said define power, what would you say? Closely, it's the rate of doing work. I'm sorry. So you don't do work if you just stand here, right? You understand? You got to generate a force, right, which causes something to change or move in direction, and you got to go a certain distance, right? You understand that? So power is the rate of doing work. So the two main formulas for power is equal to force divided by distance. That's not the one we use. Distance and speed are what we call inversely proportional, which means what? Yeah, they're opposite, right? So we can, if they're opposite, it means we can turn a division into a multiplication. So power is, we use the formula is force times speed. And then our force is going to be in voltage or volts. And then our speed is going to be in amps. And that's what we calculate power. Okay. And what is the power company trying to sell you? What's the name of they're trying to sell you power, right? You understand? So let's say I've got 1,000 watts of power. Now we can transpose this formula and I can say the amount of current would be equal to the power I'm trying to send divided by the number of volts. So all I did was just transpose this formula. So what does that mean? Alabama Power is trying to give you power. Y'all understand? Yes or no? Okay, so notice V's on the bottom. So what does that mean? The higher we make the V, the less I is required to produce that what? That work. Now the problem is the amount of voltage drop we get is equal to I times R, and everything has some type of opposition. So that means a piece of wire has an opposition. How much voltage we drop depends on what? The resistance times the what? The current. So if I make the current extremely high, if I make the current extremely low, that means my wires are not going to drop much voltage. Y'all understand that? So that means if I could use 750,000 volts, then basically I could send 750 kilovolts or 1,000 volts. Then I could send 750,000 watts of power with only 1 amp of current. If I tried to do 750,000 volts at 1 volt, it would take 750,000 amps of current. So what they do is they step the voltage up for transmission. So that way we can use, instead of using copper, which is one of the best known conductors, now they can use aluminum, right? Y'all understand that? Because the voltage is so high. So even though aluminum has a pretty good deal of opposition, if we can make the voltage high enough, we don't get very much line crew calls it line loss. That's how much loss you get in the conductors themselves. But we don't change the power. The power in, if it was a perfect system, power out equals what? Power in. Y'all understand that? Power out equals power in, because we don't change the amount of work that we do. We just do it at a different speed, right? Does that make sense? It's even like jogging. You know, you could walk 1 mile or you could jog 1 mile, and which one would, that's not, but you would burn a certain kilowatts or certain calories, right? You understand that? So if you burn 1,000 calories, you might do it 1 mile jogging, or you might do 10 miles walking to do the same calories. So what we do, we have two types of current. We have, and this is what the guy down there said. He says, well, we use transformers to step up the power. You don't use transformers to step up the power. You step up the voltage, right? You understand? The power, if the transformer was 100% efficient, then power out equals power in, right? So transformers don't change power. They change the voltage, right? You understand that? Yeah, so after that, he blew that. I said, if you don't understand the basic law of physics, where energy out equals energy in, we don't create energy. All we can do is what? We can change its form, but power in equals power out. Then, and people can't understand how can we amplify. We don't have to. We get amplification of power from a power supply, right? You understand? So that's why they call it. We got to do it. So what is direct? We have two types of currents. And current is actually what's flowing and doing the work, right? You understand that? And what pushes the current or pulls it? It actually pushes and pulls. How does that do that? We call it a power supply, right? You understand that? Or a power source is what we use. So DC, the electrons in the DC circuit flow from negative terminal to positive source through the circuit and back into the positive terminal of voltage source. Now the big problem we have with DC is that we can't readily step it up for transmission and step it down. It's very hard to do. And unfortunately, when it was introduced, this was the current that Edison decided we would use. And when he decided the first big town they tried to wire up, I think it was Chicago. You should have to check on that point. They had to put a power plant every mile. Because when they tried to send that current out, the conductors were dropping all the voltage because they can't change the voltage, right? You understand? Now, what advantage does high voltage have over low voltage? Well, the higher the voltage, the less current required to do the work. That makes sense. Okay. But what's the problem with the higher the voltage? That gets more dangerous, right? You understand? So they couldn't send, they couldn't use 1,000 volts DC to lower the current. They couldn't do that because people would be getting killed all over, right? You understand that? So I don't remember. I think they used a couple hundred volts, but now the conductors had to be that big, and they had to put a power plant every mile because the voltages were so low to produce the power. There was so much current that they had a lot of loss in their wire. So one of the big advantages of DC is hard to transmit. I mean, we can't transmit it great distance because we can't step the voltage up for transmission and then step it down. Now, what advantage does lower voltages have? Safer. Yeah, the lower the voltage, the safer it is, right? Understand that. So what do we have? So DC. Y'all use this all the day. DC generators, batteries produce it chemically. DC generators produce it magnetically. Thermocouple. We use these guys to measure heat. They produce it by heat. Solar cells. We see those all over the place now. These produce by absorbing the energy or changing the energy from sunlight over to different potential. Piezoelectric devices. Anybody that smokes cigarettes, you probably used a cigarette lighter. It don't have a flame in it anymore. If you got a real old cigarette lighter, like a Zippo, that was one of the really big cigarette lighters when I used to smoke. The piezoelectric devices creates a voltage by striking it. So that anybody that's got these lighters now, these little butane lighters, that's what you're doing. You're popping a piezoelectric crystal and generating a voltage, which creates an arc, right? We have electronically AC to DC converters. We run into these all the time. That's an AC to DC converter right there. And of course, normally we call these power supplies. Everybody's got these. Those little old bricks or cubes or whatever you call it to charge your cell phone. Your cell phone does not work off of AC. Your cell phone works off of what? DC. So I've got to have some means of taking AC and converting it to DC, and that's what the function of these little power supplies do. So electronically and bioelectric, we are bioelectric devices. We create electricity. Anybody that watched the Matrix knows that, right? What did they use us for? They used us for batteries, right? Put us in these little cubicles and hook all the stuff up to it. Used it to charge their batteries. And so these are some devices that make DC. Now, what advantage does DC have over AC? Anybody knows? Why do we have two types of power? If we could do it all with AC, we would do it all with AC.
AC has highs and lows.
Huh?
AC has highs and lows.
But what we're doing is, what's the advantage of DC? We can control it electronically. So any electronic device works off of DC. Whether you plug them into the wall or not, if you plug them into the wall, then there's a power supply in there. If you don't plug them into the wall, then they run off batteries, right? Just like our cell phone. Are we okay? So we've already talked about what the advantage is. So this is DC. So some of our programmable controllers work off DC. Some of our programmable controllers work off AC. Basically, the electronics in the PLC runs off of what? DC. So if we, some of them have power supplies built into them. A lot of them now have external power supplies. You literally have to hook a power supply up to them. We'll show you both of these. So normally when we use the term power supply, we're talking about a device that converts AC into DC at a level that our equipment is designed to run off of. Alternating current. This guy is constantly swapping directions. Now we have all types of alternating signals, but we're talking about AC being generated by a power company. It swaps directions, but it does it at a constant rate. The voltage source and an AC circuit constantly swaps direction. It causes the current to constantly change direction. Now, what's nice about AC is that all we have to do, so what we need to create a voltage magnetic or an EMF magnetic is we need to have a magnetic field. We need to have some conductors. That's all this is, conductors, right? And I can sit here all day long and put this radiator that I don't do anything. So that, but as soon as I come over and start doing this, I'm making. So if I can take this and spin it, so notice it reflects this way in one direction and it reflects this the other. If I sit here and spin this, you see what I'm making? I'm making a signal. So that's all we need to do to create an EMF, electromotive force, or voltage. All we need is three things. What do we need? A magnet, conductor, and motion. So you can see it's very easy to produce AC. All we have to do is spin a conductor, or vice versa. We call it relative motion. Relative motion means you got to have one that moves. So you can move the magnetic field and leave your conductor stationary, or you can move the conductor and leave the magnet stationary. Now, the most popular method is to move the magnetic field. So all I'd have to do if I had a permanent magnet, all I'd have to do is come over here and put a permanent magnet, right? You understand? And then I would put coils of wire up here. And then all I have to do is have a prime mover and cause it to what? To spin, and it would make AC. Of course, I would connect these together. That makes sense? Now, what we can do is anytime we put current through a conductor, it generates a magnet. I'm looking for my, oh, here we go. This will work out better. So all I have here is I just have basically a Torx wrench. But well, I'm not using it for that. I'm using it to get a chunk of metal, right? And then all I'm going to do is let me fire up my camera. Show you what I'm going to do. That didn't work. Oh, there's another one I can use that. So once we put current through a conductor, it generates a magnetic field around the conductor. And we call these things electromagnets. You see them all the time, but you don't realize what's going on. Anybody ever seen these cranes that pick up scrap metal? They swing over there and drop it down. And then they just bring them up, pick up a bunch of junk and come over and drop it down. Well, that's nothing but an electromagnet. So all we need to do this is come up here and have a magnetic field, have a current. This word's got. I should have checked my. Now, the advantage we have with an electromagnet that we don't have with a permanent magnet is that what do you think controls the strength of the magnet? The amount of current we put in it. Well, that's right. The number of windings we have, how close we can get these windings together. So this is a very poor example. So we have special wire that we call magnetic wire. And this guy is really, really thin insulation. So this is magnetic wire. Very, very thin insulation. In fact, what you can do is you can. I think it's over. It's either in 206 or 204. In fact, well, with this wire, you can strip it with a cigarette. It's a very, very thin insulation. So when we use this stuff, we really got to clamp it down, especially if we use it in AC, because AC constantly tries to create vibration, and it'll wear that insulation off. So this is not a real good example of electromagnet. It's going to be, in fact, I hope I can get enough current in it to make it work. I know it's not going to pick up that. Might pick up this. Now, what we can do with this guy is with an electromagnet, is that we can control the current. Control the field strength by the current. Another thing that we can do with an electromagnet is we can turn it off and we can turn it on. We can't do that with a permanent magnet, right? So we'll see if this works. So I think this has got a tin coated metal there. Might have to get my jumper cables, my jumpers. Yeah, one of my conductors is open. I don't think it'll pick this up. Almost. So this is an electromagnet. So that didn't have any ferrous metal in it. And so all I have to do is let it go, and then we lose it. So, So this is the advantage of electromagnet. Okay. Well, okay, I've got an electromagnet that I can control the strength of it. And so if I instead of using a permanent magnet inside my generator, I can use an electromagnet, and then what can I do? I can control its strength. So now it means I can regulate the output. So if I've got a generator and I turn on my lights in my car, it would cause the voltage to drop down, but your regulator senses that and puts more current into the magnet, right? You understand? It causes the what? It causes the balance. You turn your air conditioner on, you roll up and down the windows. If you put a voltmeter out there on your battery, which is being charged, it stays almost constant because we have the ability to regulate. But what we do, if I spin that deep field, I'm going to create AC. So AC is really, really easy to do. So what you saw, that's the way Alabama Power generates their power. All they've got to do is have some type of energy conversion. We call it a prime mover. So what's some of the ways they spin their generators? Yeah, well, basically the primary way is with steam or with water. So we have a lot of hydroelectric dams around here where they drop water through a turbine. The turbine spins the generator. That's luckily the state of Alabama. We have a lot of rivers. And Alabama Power's just got about a dam on just about every one of them. And then, of course, we can burn coal and run into a boiler to create steam to turn the turbine, or we can use nuclear heat to create steam to turn the turbine. So AC is really easy to produce. DC is not. A DC generator, we got to mechanically constantly switch the leads. Well, that's what we do. I have a special unit called a commutator, and I didn't bring one over here. These are produced by AC generators. Technically, we call them AC generators, but the problem is that when they first put generators on automobiles, they called them generators. So originally they figured out that they could do it a lot cheaper and more efficiently with an AC generator, but they didn't want to call it a generator because you had all these auto mechanics out there that didn't know the difference. They just knew generator, right? So that's when we started calling them alternators. If you're in a manufacturer, they don't call them alternators, they call them AC generators. We can produce it electronically. That's what this guy does right here. So we can convert it to DC because we can electronically control DC, and then we can take that and convert it back into AC. And some of y'all have that feature on your car. You go out and buy what they call an inverter. My wife has one, she's got a van, and it's got an inverter in it. She's got a 120 volt plug in her van because it's got an inverter. So we're electronically generating what? AC from what? DC. Our bioelectric, so this is an AC alternator of a generator. Some of y'all have one of these. I bought one of these after the big snowstorm of, what was it, 93? Guess how many times I've used it? None. I do crank it up. The AC power plants, electric eels are really, really neat. They generate about approximately 170 volts DC, but they can also generate about 10 volts AC at about 25 hertz. So they can do AC, and that's the only bioelectric guy that I do. So usually, Same eel. Wow. Usually it depends on whether they're trying to kill or stun. So they use this to stun. They use this inverters and also these devices we call function generators. So what advantage does AC have over DC? Well, AC, we can do what? We can step it up and step it down. We can change its value very easily by running it through transformers. And that's all a transformer does. Right? You understand that? Don't change the power. Everybody understand that? It don't step the power up and it don't step the power down. It steps the voltage up. If the voltage goes up, the current's going to go down from the power source, right? Y'all understand that? Don't get it confused with what Ohm's law says. We're talking about the power source. So loads are designed around a certain voltage. All your high wattage loads at your house are designed around 240. All your low wattage devices are designed around 120, right? You understand that? Where's all the 240 plugs at? Anybody get, they're hid, right? They're behind. Yeah. Or they're direct wired. Like if you got a water heater, it's probably direct wired, right? You understand? But your 240 has got to be behind the equipment. People can't readily get in there and get to it. So if you want to get to the one in your dryer, you got to pull your dryer out away from the wall, right? You understand? Also, AC is easier to generate. DC is hard to generate because we have to mechanically constantly switch that voltage. So by default, if you spin a magnetic field, it's going to generate AC. So how do we do that? Well, what we do is we put what they call commutator plates. I'll bring one in and show you to it. And it mechanically switches switches it every time. It switches the polarity mechanically though. Most alternating current provided by voltage sources change rates at a constant rate. This repetition produces a voltage waveform shown on the next slide. An AC waveform is referred to as a sine wave. We're not going to explain this, guys, even I could. It got the name sine wave because the voltage varies with the trigonometric sine of the electrical angle. So that's how it got the name sine wave. And this is the way it's generated. This is what it's sine wave. But it just constantly repeats. It just constantly repeats. One repetition we refer to as a cycle. And the rate of the cycles we call frequency. Alabama Power generates 60 cycles per second. The two main frequencies are 60 cycles and 50 cycles. Most of Europe uses 50 cycles. Both over here we use 60 cycles. Both here on the. Once you set it, you can't change it because the whole power grid is designed around that frequency. We're not going to talk about why. If it ever drifted very much, it would cause all types of problems. Because how you build your transformers, how you build your motors, everything has to be designed around a certain frequency. Well, our whole power grid is designed around 60 cycles per second. Or hertz, 60 hertz. You'll hear that used. This will go on. How long will this go on? Until you turn it on. But this is showing you. So it's generating on a circle. This is not important now. So we talk about electric. How many degrees in a circle? 60 degrees. I'm sorry, 360 degrees. And if we was to stop this, it would form a right triangle. And then if we was to calculate the sine of this angle, that would tell us exactly what voltage is. So most people say, so every 180 degrees, it goes back to what? 0. So literally, there's no current in the circuit right here. And these lights right here are flashing 120 times a second. They're 8.33 milliseconds. It changes. Okay. But our eyes, luckily our eyes, it's not really refresh, but we'll call it the refresh rate of our eyes is not that fast. Because a lot of people don't understand that movies is just a bunch of stilled images that flash up. But they do what? They flash it at a rate that your eyes can't respond to. So these guys right here flashing. Fluorescent lights flash. We don't see it. That's why when you take pictures, if you don't have a good camera, they'll appear yellow because your camera's fast enough to keep up with it. So we have cycles, we have alternations, but anyway, we're not going to get into this in much detail. But AC got all kinds of advantages. What advantages? It's cheap though. And AC motors, and we're not going to talk about why, but AC motors cost less per horsepower. So originally, we had a lot of DC motors in industry because we could control the speed precisely. Because AC motors are really, really hard to control the speed. AC motors try to change the frequency. We get in all kinds of problems when you change frequency. But they figured out a way to electronically control those things. We call them variable speed or variable frequency drives. And we're not going to get into that. This is the way most power is generated here. We call it three-phase power. So Alabama Power doesn't generate single phase, which is what you have in your house, which would be on the other one. It generates what we call three-phase power. It sends this over 3 conductors because it's more efficient to transmit. We divide the current over 3 conductors instead of 2 conductors. So if you use 2 conductors, then every conductor, both conductors would conduct the same amount of current. If we take that and divide it over 3, then each conductor would carry the current divided by the square root of 3. But anyway, so I can send a lot more power over smaller gauge wires, right? So this is pretty good. So this is why you get on these high voltage lines, you always see how many wires? At least 3. You see them in groups of 3s, but if you look, they're split out in 3s because they transmit 3-phase. So we can control this stuff. So this is 3-phase. So notice each angle, each generation, if we was to measure this, this would be 180 electrical degrees. This would be 360 electrical degrees. So they cross at 120 electrical degrees. And the sine of 120 is 1.73, which is the square root of 3. And so y'all see these all the time, right? How many main conductors? 1, 2, 3. And what type of wire do they use? They use aluminum, right? Because they do what? They step the voltage up so high. And we look at 3-phase transformers and that kind of stuff. And this is what we're talking about, is why we step it up. So over here in my house, I'm trying to get 1,000 watts of power at 120 volts. So 1,000 watts divided by 120 would be 8.3 amps. Now, how much is the power company going to give me? What? The power company is going to give me 1,000 watts. You know what I'm saying? A lot of people have problems with that. We generate power. Power in, if it was 100% efficient, power in equals power out. So I come over here and I go through my transformer. This is my transformer house. It's giving me 120 to 240 volts. We're going to do this at 120. Up here I got 2,300 volts. They say, guys, this guy here will kill you dead, right? So if you ever see a power line fall, it's about 200 volts out there. But look, now all of a sudden I'm getting 1,000 watts of power, but now I'm doing it 2,300 volts. So now I'm down to 0.435 amps. So now I can go down to smaller conductors, right? You understand? I get less line loss. Over here we got big conductors to handle that, right? You understand? Then up there I'm doing 275,000 volts. This would be interstate, not intrastate. Over here, I'm doing this at 275,000 volts. Now I'm down to 0.036 amps or 3.6 milliamps to send that same power. Now I can do what? I can drop down to a smaller conductor, right? You understand that? I can go, instead of using copper now, I can use what? Aluminum, right? You understand? Now my towers don't have to be as big, right? You understand? A lot more efficient. And then I get over to the power company. They drop it back down, 2,300. Usually power companies give different voltages. So we call these guys substations. Oh, you ever heard of that term? And that's all they're in there for, either to step it up for what? Transmission, or step it down for something. By the way, this is mine. That's out of my book. And we don't need to talk about that. So that's AC/DC. Anybody got any problems? Now PLCs, the internal electronics of the PLC runs off of DC. Now you might plug them into the wall, but that don't mean they run off of the wall. AC. Inside, it's either inside the programming controller, or you have an external power supply. You run into both of them. We got a Siemens PLC, which is it runs off of DC, so it requires a DC power supply. And then we got an Allen Bradley 1100 PLC. And, we had that built-in power. So here's this is the Siemens 1200. Here's the I have power supply. This is on a frame. Here's the actual 1100 power. Here's the 1100 PLC. Oh no, like right around this. This is one of the frames. And this guy plugs in the Alabama pump. That guy, we have to put the power supply. So some of them have their built-in power supply. Some of them use the external power supply. It all depends on what type of model and what you get. That makes sense? But the internals of this guy runs off of what? You said